All right, my video recorder crashed this morning, so I will be recording this and posting it later on. There's quite a few things that I have to do, two problems that I have to do today, and then go back to the part that I had to swallow my pride and say that my video solution was wrong for the homework that you're going to be doing. It was okay, but if I did it like that, I would lose 8 marks out of 26 on the midterm, okay? But I just posted the correction to it, but we'll go through it later on, okay? So we're going to do two problems today, one from chapter 16, and two different ways, and then one from chapter 18. So let's worry about this one first. We have an assembly problem. So I got these three pieces. I put the pin inside of that hole, the two pins, and the bottom end pieces, bottom end faces of the pin are fixed, clamped, and I take the end pieces of the top pin and move it up by 1,000 inches, something like that. So the first question is, how many planes of symmetry do I have in this problem? Remember, the bottom, the ends are fixed, clamped, and the top is moved up by some amount. How many planes of symmetry do you see there? Well, you said 3, you said 2. It looks like most people are saying 2, the ones who are answering, and I'm going to say 1. Okay, first of all, just look at stare at this thing for a second. If I cut it through the thickness, wouldn't the two sides look the same? Exactly? Okay. If I cut it this way so that it cut both pins along this vertical face, wouldn't the left side and the right side look the same? Good. Now, why am I not taking, so far it's 2, why am I not taking the middle plane as plane of symmetry?
Because you're only extending the top part, you're only playing from the top, you're not playing from the bottom.
Yes, so in principle, what I do on the top is different from what I do in the bottom. Now, for practical purposes, practical reasons, not for this course, not for writing a test, you can say, yeah, it's true, I'm applying some force up there to move it up by 1,000 of an inch. And that clamp is holding it there by applying the same force in the other direction to keep it in place. So can I not view this block as being pushed up by some force and pushed down by the same force essentially? And could I not take the middle plane as a plane of symmetry? Not for this course, but you're very close to actually accepting that, and that is correct. In this course, 2 planes of symmetry. Now, if I pull this thing up by 1,000 of an inch, and my friend also pulled this thing down by 1,000 of an inch, then this middle one is a plane of symmetry. Okay? All right. So I will do the first way. In the book, this problem is done without any planes of symmetry, but I will use 2 planes of symmetry. For us, the third one is the same thing. You just have to make a third cut and then put surface sliders there. Okay, so let's go ahead and make it. You start with a product file. New product file. Okay, let's make the block first. Okay, so insert a new part in there, and I will call it the block. Right-click properties, block. I'm not going to bother changing the instance name because for the simple problems that we're doing, really is not that critical to do that. So we're going to make it. To make it, you have to go to the part design. I double-click on this line, on this block, and it put me in part design. So in a convenient plane, for example, on this plane, I will sketch. By the way, I'm not going to worry about dimension. I'll just look at one dimension so that I can orient myself, but I'm not going to make sure that these are the same thing as in the book. So because the plan is to cut it with different things, I might as well use a centered rectangle so that if I want to make a cut later on, at least I have the right plane in there. Let's put some dimension just so that I can see how big these things are. Okay, 10 inches, 10.8, that's fine. Now, I'll draw a circle here, a full circle there. That's where the pin is going to go. And I need the same thing down below, so I can draw it and make sure that they're the same distance, or you can actually mirror this thing. So there is the mirror thingy here. It says mirror this with respect to that, and it's going to be right there. Okay, so exit, and then we pad it symmetrically because the plan is to cut it. Look, if you have to do this problem, it's entirely up to you whether you want to make half of this thing or a quarter of it, or make the whole thing and then cut it. It really doesn't matter. Whatever is easier for you. I'll make it 0.5. Okay, there we are. By the way, notice that all of these problems say on the test and here, use the most appropriate element and all applicable planes of symmetry, or the wording may be applicable finite element planes of symmetry. Okay, same thing. Now, as far as most appropriate element, most of us are going to do this thing with solid element and the pins with solid elements. Okay, and that's fair. That's the way I did it for you in class when I'm doing it. But there may be one or two people who decide to be different. Okay, and that's perfectly acceptable. And I'll look at your solution. If it makes sense and if it's right, I'll give you a mark. For example, somebody might try to use this thing as shell with a given thickness, and the pins as beams. It is possible to do it like that, and you can get fairly good results, but make sure you're doing it right. Okay? Anyway, but this is fine, the way we're doing it right now. We're going to make everything out of steel. That being the case, I'll apply the properties to the product at the very end. So I'm going to insert the next part, which is going to be the pin. So I'll call this thing pin. I'll change it. I'll change the name right now. Properties pin. And it doesn't matter. We can call it the top pin, bottom pin, or a pin because they both look the same. And to make it, you go to the part design, double click on the pin. You're already there. And on a convenient plane, on that vertical plane where I did my original sketch, I'm going to draw a circle that size. But the easier way is to project that circle. Wait, I have to go to the sketcher first and then project. Right. I'll go to the sketcher and then project that circle. That's entirely up to you, but we can go and draw it and then mention it, etc. Exit, and then pad it. Mirror extent. Let's make it a little longer. Okay, that's good. As far as the other pin, you have the same option. Insert a new part and go make it, or you can copy and paste, or you can save the entire product and use this pin as an existing component. And I told you why you may want to do that, because if you have 100 of these pins, then to make each one of them either as copy or paste or actually literally making it will take resources. Okay, but if you do it as an existing component, there won't be any resources associated with it. So what I'm going to do is I'm going to copy and paste in the product. Notice that there is another pin here, and sitting on top of that. And by the way, notice that it says 1.2 because this is an instance of this pin. Okay, it's not an actual part. I'm sorry. This is a copy paste I did. It's a different part. Right. Now, okay. So let's go ahead and I'm not going to even bother saving. That's a bad idea because I may regret it in a few minutes. You never know. Okay. So first of all, we're going to put these things in place. In other words, assembly constraints. So let me move these things apart. Not that. Move and manipulate. My favorite one is here. I'm going to move this. I don't know. Maybe I'm going to move that guy, etc. If you don't have any assembly constraints on the assembly, you're stuck. I mean, basically, this is what you've got. If you want to solve this thing as a finite element, you can't do it like this. You have to put it in the right spot. So I will put assembly constraints in it so that if I ever have to do something like that, I update it and it goes back where it is. And my suggestion was first you fix something, anchor something. So you click on that anchor sign, you click on the block, so block is fixed now. Okay? And then I move things relative to this. For example, let me also do a little bit of rotation because you're going to see that that can ruin the party. Okay, good. All right, first of all, I want to put this pin on the top. So coincidence between this axis and that axis and update. There. But I can move this thing sideways and it's going to stay there. For example, if I translated this, translated say in the x direction, I'm stuck. Okay? So what I'm going to do is I'm going to make a coincidence between the vertical plane of the block and the vertical plane of the pin. So these sit on top of each other, and when I update, it's going to go back. Even if I took this around, did some weird rotations to it, instead of update, it goes back where it is. Notice that on purpose I rotated this a little bit. You'll see why. So let's do the rest of it. Coincidence between this axis and that axis. No problem. Update. It's already there, lined up. And coincidence between this plane and the vertical plane of the block and update. Okay. If I move these things apart, any weird rotation, update is going to go back to original condition. But I did rotate the bottom one. You'll see what the implication of that is. So we're going to cut these things in the assembly at the same time. There's a saw here. You click on it. And you say it's asking you, sometimes you wonder why is it waiting? What are you supposed to do? Well, read the bottom. Read the bottom here, bottom left corner. It's a selected plane that you want to basically cut it with. It can be any of these vertical planes. And it says, if I cut it with that plane, these parts are affected. Are you sure you want to include all of them? And the answer is yes. And which side do we want to keep? We really don't care. And there we go. Notice that it did a cut like that. I'm also going to cut it vertically. Let me move this thing. I will rotate it, but a different rotation type. Okay, so let me move this thing, this bottom pin. Let me move it out. Let me move it out. Let me rotate it, for example, about I don't know, y-axis. No, about the y-axis. Ah, that's what I wanted to do in the first place. But if I update, it's going to go back where it was. Okay, watch it. It's going to go back where it was. There is no problem. But now I'm going to cut it with a vertical plane. Now I'm going to cut it with a vertical plane. So saw, vertical plane, this other vertical plane, all of them to be affected, and say okay, okay. What I wanted to show you, it didn't come out the way I wanted it. This thing was actually tilted. Okay, one of them was tilted. It happened this morning because of some other rotation. Don't worry about it. We're in good shape now. If this thing was tilted, this bottom one was still tilted, it's still in that hole. But it was tilted, then put another constraint so that it's flush. I was unable to show you what I intended to do. Fair. Let's go there, apply material on it. Oh, where is it? So right there, apply material. Metal, everything is made out of steel. Good. Okay. We are pretty much done here. Now we're going to go to generative structure analysis, static analysis. Somebody asked me in this course, do you do any dynamic? We did it only once for that natural frequency calculation. You can do dynamic analysis for really dynamic stuff, things that move as a function of time, etc. But we are not doing it in this course. Okay. Everything that is static, except if you ever get a natural frequency calculation, you should be prepared for it or answer questions, whatever it is. Now, let me change the rendering here. Good. If I look at the mesh, the pins have a smaller mesh because CATIA looks at the size of the object and based on that come up with a, default size for that. The block is too big, so it uses this. Now, obviously, to get good results around the hole, you must do mesh refinement. Okay, I'm not asking for that. I'm not doing it here, but we have done it several times, and you should be able to do that. Deactivate this with this guy in front of you. There's nothing you can do. Let's go and apply our restraints. So now you have to be very careful here because if you miss any of these, that means you're rushing. Don't rush. Okay? Unfortunately, you're going to miss whatever point you have for that restraint in format, or for you did everything except for one. Unfortunately, you're going to lose all of it. Okay? So let's do a surface slider on this, on that, on this, and you can turn it around if you feel like doing it this way. That piece, this piece, don't forget that guy, don't forget this guy, okay? So this is the symmetry restraints, and then this end is clamped, does not move. This other piece, we are moving it up, therefore I have to make it 0 up. That's the way it works, and then you can change it. So coincidence, not coincidence, user-defined restraint on that face in the direction Z, direction Z means 0. It's 0. This thing means 0 value. And once I do that, then I can change it by using enforced displacement. Either you pick it from the screen here, or you pick it from the tree there, the correct restraint, which was the third one, and you give it 0.01 plus 0.01 upward. I don't know whether it was 0.01 or 0.001, whatever I asked you. 0.01, okay, good. Do not divide 0.01 by 2. It happened last week. Somebody was dividing. Okay. All right. If I run it, obviously it's going to crash because the pin doesn't know that there is a block there, etc., etc. So you have to create those connections. So for the first one, I'm going to select this. For the second component, I'm going to select the inside of the hole. Now, to select the inside of the hole, unfortunately, there is no way but either deactivating this, but not deactivating, hiding it right there, and do another one. By the way, because you made a copy and paste, look at you hid one, the other one also was hidden. Okay, so if that's bothering you, go make the other pin. If that's confusing you, go make a pin. Don't do copy and paste, or even insert the existing component. Another one. First component, the hole here, and the order doesn't matter because notice that before the previous one I did the surface of the pin and then the hole, whatever is convenient is sitting in front of you. And for the second component, it is the surface of the bottom pin on the side. And we say, okay, you can bring this thing out. Some people feel like doing that, you don't have to. And these connections that I created, if the problem clearly states that the pin and the block are perfectly glued together or bonded together, then you make this thing faster. If it says the top one is glued, perfectly glued, you just do the top one. Otherwise, contact. Okay? So it's the contact, you bought it and you stuck it into the hole. That's pretty much it. You didn't do anything. So that's a contact condition. So there's the contact. From here, do not fool around with these numbers. If you're doing it, better be right. What's the other one? Again, contact. for this guy, okay? And I'm pretty sure we did everything. By the way, I just want to point out to you that if I had not used the plane of symmetry that cut the pin into two pieces, remember lengthwise, it cut it into two pieces, the pin could slide out, so you have to take care of that. But because I cut it with that vertical plane and put surface slider, it cannot slide out. Okay, just be aware of the fact. Okay, let's run it. Couple of comments. In the morning lab, towards the end, the student showed me something that when he was trying to run this, don't worry about that, that's the common message, this thing ran. But when he was trying to run this thing, it got this error message. And there is nowhere, no one in the world who reads that knows what the hell it's talking about. Probably the only person who knows is the person who wrote the code and decided that if something goes wrong, this is the message. It's nowhere in the manual, and there's no way you can fix it. What I suggested to him is, first of all, did you save? He said yes. Let's get out and back in. So got out, close Kalkia, everything back in, run it again, same message. So at that point, you're doomed, basically. In other words, hopefully you have saved your product. Forget about analysis, just throw it away. There was no way we could figure out what the issue was. Kill the analysis, just throw it away. Do another analysis. I mean, yes, you kill a few minutes, I understand, but that's the only way. Now, so if you look at the marking scheme for the homework that you're going to do today, which is very similar to what was done last year, this is the problem from last year. It says, if it doesn't run, automatically you lose 35%. Okay, that means either you didn't manage your time properly so that you couldn't go back and do another one, or you did a few crazy things that you can't fix it because it is, for example, if there are two loads, hypothetically, two loads in there, one of them has an exclamation mark because you deleted something, but the load is sitting there, it doesn't know what to do, etc. It won't run. Okay, that's easy to spot. But sometimes when you get runtime errors like that, there's no other way. Anyway, yes, you do lose 35% because it didn't run. You're giving me something after 6 weeks that didn't run, okay? That's okay. I will go through what you have done. Did you have the symmetry correctly? Okay, did you have the restraints correctly, etc. Then you got 35% of those things. In other words, you get part marks, but because it didn't run, sometimes it may not be your fault. Like this guy's, I don't know, no, everything looked okay. Anyway, there we are. This is the situation. This is going to deflect, and obviously this is right. Let's just say this is right. It's doing what you expect, right? Let's zoom in. It's doing what you're expecting. You take the spin, pull it up, it's going to look like that. You can plot the Mormisa stress, you can plot the displacement, etc. But let's find the force. Let's find the force. Okay. I want to know how much force is needed to pull this thing up 0.01 inch. So the process is you go here, right click, under sensor, right click, create resultant sensor, reaction sensor. And then it says, okay, you want to create a reaction sensor? Tell me where. You have two choices. You can select a clamp at the bottom, the two ends. Not just one of them. Just two of them, both of them, okay? Or you can select that restraint on the top that you pull this thing up, okay? Now, so let's go and do it from the tree. This guy, I'm choosing this. I'm choosing this, okay? And then update. 3,172 pounds. Multiplied by 4. Yeah, multiplied by 4. Okay, because this is only for 1/4 of a model. 1/4 of a model. Don't get the impression that everything you cut something by 4 times, you have multiplied by 4. I mean, these things depend on the problem, depending on what you have done. And do not, I mean, obviously on your paper that you're going to give us, you're going to write this times 4. Do not cancel that, because when it comes to marking, I have no idea where you got that number from. Because if you say okay, it's going to be in the tree. I can check it and see where you got your number from. All right. Any questions? Yes. Halfway, right? Let me put it this way. If you didn't do the planar symmetry on my side, okay? Right now, no, sorry, the back side. If you didn't do the planar symmetry on the back side, that's going to be, the pin is going to go all the way through, right? That pin can come in and out. So you have to fix it. You have to fix that issue. And the way to fix that issue is that face where you apply the upward zero value that you change it, you have to say no displacement in x and y direction. Okay? That's the only way to fix it. Because if you do only one of them, you can spin in there. So yeah. This is the best case scenario. You don't have to worry about those things. If you look at the book, this is done without any planar symmetry, and issues like that come up. Okay, you may want to check it if you want. Anything else about this? Okay, let's kill this. All right, so let's go to our second problem, which is this situation. You have two different metals somehow perfectly bonded together. You really cannot do surface welding of metals. Surface welding means that, seam welding, you put the metals like that, you seam weld around them. Or spot welding, dot, 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 Theoretically, we should be able to do surface welding, but it cannot be done. We put adhesive there, or some kind of adhesive. It's not a weld anymore, okay? But we still call it. So these are perfectly bonded. Perfectly bonded means that they're fastened together, okay? Now, one end of it is clamped, and we take the structure and raise the temperature by 400 degrees. Put it in the oven. Put this thing in the oven. One end of it is fixed. Maybe attach it to something really heavy and then put it in the oven. Okay, so the question is, what will happen to this thing? It's called a thermostat, actually. This is the mechanism behind the thermostat. Because what happens is that it moves one way and establishes contact with another piece. The current goes through it, so that becomes a thermostat. But tell me, how is this going to, if you put this thing in the oven, what's going to happen? What does that mean? So, bends, right? You're saying it bends. The question is, does it bend up or does it bend down? You're saying bend down? Yeah. You look at that bend down, okay? Any other suggestions? You're saying it bends down? And we don't know, let's find out. Let's find out. What does it have to do with? Coefficient of thermal expansions are different, okay? Aluminum is more, but we don't know what you're saying is right or not. We'll find out, okay? Now, this problem, by the way, does have a planar symmetry, so I don't have to do the whole thing. I can just cut through the length, not that, don't separate the two. Through the length, but in the book, this is done, but without any planar symmetry. I'm going to cut it. So let's go ahead and make it. Yeah. Product. Insert the top piece is aluminum, so insert new part in there. I'll call it top, I'll call it aluminum, properties. Okay, maybe top aluminum, how about that? Top aluminum, okay, good. Let's make it. Nothing can be easier than that. So on that horizontal plane, I will sketch. You have a choice of making half of the piece and pad it, or you can make the whole piece and cut it. It's entirely up to you. Split it. So I'll do half of it. I'll do half of it. You understand what I'm saying? You don't have to make the whole thing and then cut it with a plane. If you want, you can make half of it because you know that you're going to be cutting it anyways. So this is 10 inches. I believe this thing was 0.5. What was it? Was it 0.5? 0.5? Maybe that was not 10 because that figure, 6. That was 6. This guy was 6. It just didn't look the same as the other guy, 6. That's better. Okay, exit. Now I'm going to pad it up by half an inch. Yes. Because it bends. Okay. If both ends were fixed, the second plane of symmetry is in the middle. Yes. Well, if it's fixed, it won't go anywhere on both sides. It bends in the middle. It goes like this. It goes like this, or it goes up, depending on how things. So we padded up by 0.5. That was the thickness of that top strip. And we're going to put, actually it was, what was this? 0.25. I know these things don't look right. 0.25. 0.25. And we say, okay. All right. So we put aluminum properties on it. So apply material. We are in part design. We have to be in part design if you're going to put material on parts. Okay. So aluminum on the top. We say okay, and we close it. Now we're going to go to the product and insert our second piece, bottom steel. So insert a new part. Let's change the name. Right-click properties. Part number, part name, bottom, steel. Say okay. So let's make it. On that bottom, on that plane where we drew the aluminum piece, we draw. Can you tell me a fast way of actually making that bottom piece? Project it. Project this piece. It's going to be right there. You can see that, right there. And then we're going to exit and pad it in the opposite direction. Okay, reverse direction, 0.25. And this is going to be made out of steel. So apply material on it. Metal, steel on that part, and we say okay. I like to change the color also. No reason, particular reason. I'm going to make it red, but I caution you that red is not a good idea because sometimes when things don't update or whatever, it becomes red. But sorry. Okay, so that's it. So let's go ahead and generative structure analysis. CATIA sees two parts, immediately it meshes it. And these are gigantic elements through the thickness when you think about it. So let me make this thing a little bit more respectable. Maybe up here, maybe 0.1 for the top one and 0.1 for the bottom one. 0.1. At some point, somebody is going to ask you, what is that sag there? We'll worry about that later. The size of the element, you understand. Sag, let's not worry about it right now. Now, this will, we can run it, there's no problem, except that just be aware of the fact that you need a fine mesh at the interface because material properties are different. Stresses are going to be changing rapidly at the bottom and the top pieces, so this is not going to do it, but we're not going to worry about that. Okay, so what else do we have? We have these ends clamped. Okay. Don't forget the surface slider because you cut this thing either on this side or that side because it really doesn't matter to us. this piece and the bottom piece. Okay. All right. Now, we want to put this thing in the oven because what makes this thing move then is the load is coming from thermal effect. Okay. So whatever you're trying to do, look in the load, whatever. And if you look at the load, you see this colorful thing. I'm sure you're familiar with this kind of a icon, temperature variation. Remember that? Or I don't know. You click on it, and it says, okay, you want one of these parts to be subjected to temperature difference, okay? Pick it. Well, I'm going to pick it right here. That's the top one. And as soon as you do that, it puts a T up there. So that top piece is going to have a temperature effect associated with it. And you put that number there. Temperature rise. That is 400 degrees Fahrenheit. Okay? Now, rise from what though? That's the problem, because these coefficients of thermal expansion that you find in tables, they are at a particular temperature, okay, whatever that temperature is. For example, if you looked in a book and you found aluminum has this temperature coefficient of thermal expansion at room temperature, for example, 80, just hypothetically, you have to tell the software that that number alpha that you're giving it, or it's in the database, is at that room temperature. Because we don't know what that coefficient of thermal expansion is, at what room temperature. It's probably 72, 75, something like that. So watch this. I'm going to close that. I'm going to close that. And as soon as we did temperature, something popped up in this line. This environment, you have never seen it before. But as soon as you did temperature, it popped up. And you click on it, it says initial temperature, room temperature. So if my initial temperature, as described in here, is temperature rise of 400, above the room temperature of 75, you've got to change that number to 75, okay? So 75. By the way, I have changed my unit so that it's in degrees Fahrenheit. If it's in degrees Kelvin, if you haven't changed your units, it's going to be in degrees Kelvin. So you can type F, but it's going to convert it to Kelvin. So that's fine. And oh, I wanted to do the bottom one too. The bottom goes in the oven too. So let's go to this thing. I can do it again, or I can go there to load. Double click on it. I forgot to select the bottom one. So two bodies, put in the oven, raised by 400 degrees from whatever the initial temperature was, room temperature. Okay, so let's run it. Don't worry about that. So I'm going to plot the deformation for you. Displacement. How about displacement? Wait a minute. I'll do it from here. And this is pretty much where my system crashed in the morning. Oh yeah. I don't want to do this again. That's exactly where it crashed last time. But let me destroy it. Okay, right there. Can you see what's going on here? Didn't you say it's going to bend? Well, look at what happened. That top piece just moved out. The bottom piece just moved out. So why is this happening? Yeah. You have to say that these are perfectly fastened. We didn't do that. It's just two pieces that are expanding in space. It goes like that, it goes like that. Okay? So we deactivate this plot. We deactivate this and go and create our connections. Connections hasn't crashed yet. So let me hide this For the first component, select the top face of the, in this case, steel. For the second component, the bottom piece of the aluminum. And this is going to be perfectly bonded, means it's going to be fastened. If you make contact, they slide on top of each other. Unless you go and put a coefficient of friction and say don't fool around with it and stuff like that, or there's a check mark there, no sliding, don't do it. Okay, so let's go here. This is the thing that I created. This is going to be fastened. This is the connection that I created, and it's going to be fastened. So let's look at this for the fasten. Face connections. By the way, you see, when you look at the connection properties, there's two toolbars that we're going to be using in this course. These are the two. Face that we have used it several times. Distance, we're going to be using it extensively next week. But these last two, which are welding, we're not going to do anything with it. Okay? And so we're going to make it fastened on there. And it puts the fastener sign here. And for those of you who have been paying attention to this fastener that shows up on problems that we have done so far, pretty much all the times that we have done it, there was a big box and the fastener was inside it. Or there was a big box and the contact thing was inside it. Or the big box where the prick maybe shrinks it. I said, don't rely on that big box. There is no big box there. It depends on your connection, what you're doing to what. Here I did a surface to surface, and this is how it came out. Do not count on a big box and the fastener inside of it. Okay, let's do a run. Okay, let's look at the bending. You said down, right? Anybody up? You go up. One up, one down. Down. Because the aluminum wants to expand more. The aluminum wants to expand more. The steel says, no way, you're going to go with me. So it has to go down. Okay, otherwise it won't happen. Now, a couple of things here. Notice that I have generated two different plots here. As a matter of fact, let me also do one for deformation. So I've generated 3 plots. We'll see. Every time you generate a new plot, whatever is already there is going to get deactivated. Now, if you want to put these things side by side, and I'll tell you why I'm asking this, you have to activate the stuff that you want to put side by side. If you want to put all 3 of them side by side, no problem. Activate all of them. And we're doing it. Okay, good. And the other one? And they're all going to be sitting on top of each other. So if you want to put them side by side, you go okay, you go here, you see, when you have an animation, I mean, the fifth one, the second one from the right, it looks like 2 things next to each other. So that's side-by-side contours. That's what it means. You click on it, it says, okay, in what direction do you want to put these side-by-side? In the X direction or Y direction or Z? Let's say you want to lay it in the X direction, like this. X. It say how far apart you want them to be. So let's make them, I don't know, 3 inches apart. It says 8, so I'll make it 3. And say okay, 3. This is struggling. My computer is struggling. So if you turn this thing around, Maybe I laid it in the wrong direction. Or did I say X? That's what this. I should have said Y. Because X is going to be, they're going to run into each other. That's what happened. So I should have said Y. It's going to be nice next to each other. Uh, okay, so see, that was a bad idea. They're there, but it's really not what I want. Let me try it again. I have a reason that I'm telling you this. This, by the way, this issue of going into coma has something to do with that recorder. Okay, it's not. These are Mickey Mouse problems. They should not matter. Listen, I'm really sorry. Every time I try to rotate, it goes to coma. So this it allows you to put stuff next to each other. Okay, uh, three plus next to each other, contour graphs. Because in the past, I have done it. I ask you to generate these three contours on the screen during your test. And how can I verify that actually you have done it? Because this thing goes away as soon as you do this thing, it goes away. I say, take a screen capture of what you see on the screen, save it as a PDF or a JPEG, and attach means dump it wherever you're supposed to put the rest of the stuff. You should be able to do it. I'm not suggesting you will or I won't. But anyway, and then this is going to coma right now. So I want to say a few words about the homework problem. The homework problem that should be available to you, you probably already know what it is. That's fine. The solution is already up there. The correction is already up there. It's a shrink fit problem. It comes from last year's midterm. And let me put this thing in the proper mode. See, it's not doing what I want. You know what? Let me first, let me keep it here. Okay, so just bear with me for a second. Okay, I can't do what I was planning. So the way I did this thing as the initial solution set that I posted for you, 90-degree sector is vertical is the plane of symmetry and horizontal is the plane of symmetry. So that green line, vertical, green line, horizontal, you could have taken it like that. So there is two half a circles at the edges. You can also do the red ones, 90 degrees. But there's only a full circle on the top. Both of them are acceptable and correct. The problem is that it's not the smallest piece that you can take. And that was the intention of, it will be intention of the test on midterm, the midterm of this year. So, the smallest module is that 45-degree angle that you see there on the left. And unfortunately, when I was talking to a few people, I was not thinking. I said, oh, you can also take it 45 degrees like that with the hole there. No, that is not right. Because if you look at the one on the left, you repeat it 8 times, you get the structure. But if you take the one on the top and you repeat it 8 times, you get extra holes. You get extra holes in there. So for today, I don't, as far as the GAs go, they don't care which one you do. You do this or you do the wrong one. Wrong one means I'm perfectly happy with losing 8 marks on 26. It's not wrong. It's not the smallest piece that you're supposed to take. And when you're dealing with use all planes of symmetry, these are all finite element planes of symmetry, which is, kind of different from geometrical planes. Anyway, any questions here? The GAs don't care which one you show them. And this thing is going to be available to you. If you don't have it, Go, the solution is posted on YouTube. You can start working on it because that thing does not come until 2:30, the actual problem statement.